So if I go to the next page, let me know if you're also seeing that. Are you able to see that?
Yes.
Okay, thank you.
Yes, we can see.
So welcome to this class. It has been a long time, and I was hoping that I was thinking of planning that we should have a very long class. Like we should finish all the slides in this in today's lesson, but I don't think we are going to manage to do that. So let's just cover as much as we can and see where we'll end. Yeah. So today we are looking at the fluid flow. Fluid flow. Last time we were doing hydrostatics. Today, that is the study of fluids at rest. And then we are looking at two things. One, the pressure experienced by submerged objects, and also the point at which that pressure acts. And those were the two main concepts under hydrostatics, the study of fluids at rest. Then today we're looking at the fluid flow. Okay, so we'll be looking at different things concerning the flow of the fluids and also the description of the fluid flow. So the motion of the fluid is described by two many ways. The first one is this one here, the Lagrangian method. Okay, so you use this one to describe the fluid motion. And the second one is the Eulerian method. So we have Lagrange and Eulerian method of describing the fluid motion. 1 and number 2. So there are two of them. Lagrangian and Eulerian method of describing the fluid motion. So we are first going to look at the Lagrangian method and also the Eulerian method. So the first method, in the Lagrangian method, the observer concentrates on the movement of a single particle of a fluid. Okay, so you concentrate on the movement of a single particle of the fluid, and then you study, one, the velocity, number two, the acceleration of this particular fluid particle that you are observing. Okay, you study the acceleration of the fluid particle and also the velocity of this fluid particle. And remember, there's a relationship between velocity and acceleration. So velocity is a rate of change of displacement with respect to time. Then acceleration is a rate of change of velocity with respect to time. So if for a given distance, velocity is given by the change, okay, in the distance divided by the change in time. The change in time, we say t, in time t. But acceleration is given by the change in velocity over the change, okay, in time. So before we go down further, let me just talk about these two concepts. The velocity, we said that velocity is the rate of change of particular distance with respect to the change of time. So now this kind of changes, these are called discrete changes. Discrete changes from one interval. So this change in x means that there was a change from the final point of x distance minus the initial point. Also the change in time, because remember, if you have distance from this point to another point, and you call this point as x0, the initial point, and x1, the final point. To find this change here in displacement, to find this change, what you do is subtract the final point minus the initial point. This is the meaning of this change. The same with time. The change in time is given by the change in time from the initial final point minus, let me write that is supposed to be minus actually. So minus to the from the initial point, the change in time. So this are discrete changes, so from time t0 all the way to time t1. So now if you want to find an instantaneous change or velocity, this is denoted by velocity dx, okay, the change in the distance over the instantaneous change in time at a particular instant. So this is called instantaneous velocity. Okay, the same with acceleration. Okay, the change in velocity over the change in time. So but we find instantaneous acceleration dv dt. So this dv dt, this is just an operator, okay, to imply or to mean that this is an instant change, an instantaneous change. It is nothing, it is just an operator or an indication, or the way we write when we are indicating that this is an instantaneous change in velocity and also in velocity and also in distance. Okay, so we're talking about this. Where is my acceleration? Yes, so now we are saying that let the position of a particle be a, b, c, d in space x, y, z. So we have let's say a 3D space, with x coordinate here, the y coordinate and z coordinate there in space. Suppose we have a particle at this point corresponding to the change in space along the x-axis and also corresponding to the change along the y-axis and also corresponding to the z-axis. If we have a point like this, let it be described by these three coordinate systems. Let us find the velocity of this particle. Okay, how are we going to find? So the velocity of this particle will be given by the change, okay, along the x with time. But remember, this is not just one distance. This is a 3D, a three-dimensional, a four-dimensional space. This is a 3D object, okay? So there will be a change along the x-axis. There will be a change along the y-axis, and then there will be a change along the z-axis. What do we get when we how do we get that velocity? Okay, so the velocity will be given by the velocity along the change along the x-axis will give us the velocity along the z-axis. Remember, this particle is in 3D, okay? So there will be some amount of change along the x-axis, okay, with respect to time, and this will give us the velocity along that direction, the u. But there will also be some amount of change along the y-axis. This will give us another velocity, the v. There will also be some amount of change. It could be along the z-axis. It can go up or down. Let me just indicate up there. This will be indicated by the velocity v along the z-axis, or with time. Okay, so when you find the change, how do you find the change along the x-axis? We say that okay, I'm getting some feedback. Remember this particle. I'm getting feedback. I don't know if it's from me or okay. So this is a 3D. It is in, okay. We have three space coordinates and time. So there will be a change along the x, along the y, and along the z. And also, okay, let's stick to this first three. So if we only add, let's say, one space coordinate, then the change along, then the velocity, okay, will be given by the change in x over the change in time. But here we have got 1, 2, 3 space coordinates. So we're going to find the change in x, the change in y, and change in z. And all these changes of this one particle are called partial changes. Okay? It will change partly in x, partly in y, and partly in z. So the change along the x-axis will be called a partial change, okay, of a partial change, okay, with respect to time. This is a symbol. This symbol here shows it. This is what we call partial change. Okay, partial change, or in other words, this partial change is also called the partial derivative. Okay, partial derivative. So it is the change along the x-axis is given by, let's say, the velocity u, to give us the partial change of x with respect to time. Another velocity along the y-axis, let's call it v, partial of y with respect to time. Another one along the z-axis, let's call it w, partial of z with partial time. So these are called partial derivatives, and they give us the velocity components of this particular particle. Okay, this is a particle here, and we have these axes. So it is changing along the x, along the y, and along the z. It is going up or down along the z, and all these changes are called partial derivatives. So partial derivative along the x-axis, partial derivative along the y-axis, partial derivative along the z-axis. And this is the same particle actually which is moving in all these directions all at once. Remember, when you're moving, even as a human being, you don't just move in a straight line. We move a bit to the left, we tilt a bit to the left, and then as we are walking, we are bouncing up and down. That is the indication of the movement along the z-axis. Okay, you move a bit to the left, bit to the right, and also you're bouncing as you are moving up and down. Now, if you are a particle suspended in the mid-air, you discover that the particle will not just move in a straight line. Okay, to move a bit to the left, a bit to the right, and also a bit either up or down. That is the movement we are talking about here of a single fluid particle. Okay, so these are the velocities. The one that describes the velocity of the particle along the x-axis is given by u, y-axis given by v, and z-axis given by w. Now remember what we said, that acceleration, when we find further change in these velocities, okay, we obtain acceleration. So if you differentiate, okay, so from this we can say, we can find the acceleration along the x-axis. Let's name it ax. This will be given by the change in u over partial derivative with time. Okay, and then also the acceleration along the z-axis, the y-axis, will be given by the change in v over the partial change with time. Okay, plus this also the acceleration along the z-axis. This will be given by the change in w, change in with time. But we know u, and we know v, and we know w. So let's find those ones. T times what is our u? Our u is given by the change in x over change in with time. This is our u. Then ay will also be given by the change change. So here we should have, what is our v? V is the change in y over the partial derivative. Then what is our az? This is going to be az. This is, we have change in z over change in time. Okay, so for the first one, the first part, our acceleration along the x-axis will be given by this. Let's evaluate this part here. We're going to get two of these partial derivatives with this x over here. Down here we'll get, okay, so this is an indication that you are differentiating, okay, distance, displacement, 2 times, this is a 2, okay, partial 2 of x, and then you are differentiating it twice. The same way here, the y will be, you're differentiating twice the displacement with respect to time, twice. Also z, you differentiate twice with respect to time. Okay, so if you get, if I give you displacement and I ask you to find acceleration, first of all, differentiate once to get the velocity, differentiate the second time to get the acceleration. Okay, so this is what we get here. This is the velocity, the acceleration for the x-axis, for the y-axis, and for the z-axis. Now, if you have the velocity components, okay, these ones here, and the acceleration components, you can find the resultant, one, velocity, and the resultant acceleration. Because remember, Lagrange, we are looking at the movement of the fluid, particularly the velocity. We're looking at the velocity and the acceleration. So if you have these components of this particular particle, you can find the resultant velocity or resultant acceleration. If you have a particle and then if you have let's say a bow, then you tie 3 lobes to that bow and then you pull them at once. They might have those, if 3 people are pulling, they might pull with different forces, and then at the end of the day there will be a direction in which that ball is going to move, and that direction it will be the resultant direction, and also it will accelerate from that point to it will move from that point to another. As it moves with a particular velocity, it is going to have a resultant velocity, and also therefore it should have a resultant acceleration. So the resultant velocity, given the velocity components u, v, and w, will be given by the square of all the sum of the squares, the square root of the sum of the squares of all these components. Okay, the square, then square root. So this is can be written also like this to show that this is a resultant. Okay, the resultant acceleration. So this square root of the sum of the squares of the components. So this is very important. This is also very important. So if I give you, if I ask you to find the resultant velocity, the first thing to think about is where are the velocity components? Where are the acceleration components? You find them, then you solve for this. So now, what are some of the disadvantages of using the Lagrangian method to describe the fluid motion? Number one, the first one is that, remember, in a fluid system there are so many particles. So if you're studying one single particle at a time, how many equations are you going to come up with for the rest of the, I don't know, other million particles? So it becomes complex and complicated to describe the motion of a fluid using the Lagrangian method. Okay, it is cumbersome and becomes complex, and the equations of motion become very difficult to resolve and solve, because you move from one particle to another, also understand its direction, this one, understand this one, and then there are millions of particles in that fluid pocket or parcel. There are other particles. Now how can you manage to understand all of them at once? So this is suitable for understanding single particles, but when it comes to a fluid parcel like this one, it becomes very complicated. So this is one of the disadvantages of using the Lagrangian method to describe the fluid motion. Is the class rep in this class? Okay. Next, let's look at the Eulerian method of describing the fluid motion. This is the commonly used method of describing the fluid motion because it looks at the entire fluid parcel, not just on the single particle. And also we'll look at one, the velocity and acceleration of the fluid motion. So if you are given the velocity component of a particular fluid parcel, okay, if you're given these velocity components here, we can find the acceleration components from these velocity components, okay, using the fluid parcel. So in fact this one, where is this one, all the velocity components are given like this. Okay, so if I were to ask you to find the resultant velocity, just square these and then sum them up, find the square root. Okay, yeah, so let's look at this. Let's find the acceleration, okay, for this first velocity component here. Remember, this velocity component u is given by, it's a function of x, y, z, and time. So to find the acceleration, you must find the change in x of this v and time of this particular particle. So to do this, we establish, or we come up with, we find what is known as a total differential. A total differential. Okay, so how is that the total differential work? How is it found? You find the change in u will be given by the partial change of u with respect to x times the small change in x plus the partial change in u with respect to y plus, or times, who can predict what should come here from the pattern I've just written here? We have the partial change x times dx, partial change y times dy, plus what should come here? Who can predict? I'm waiting for a prediction for this pattern. Hello? You might find there are no people in this class. Okay, I see Maurice, I see
Yes, we are following.
Charles, I see Esther, I see also Rachel. So I'm asking that who can predict what will come after this? So to find the total differential, I say du change in u will be equal to the partial of u dx times the change in x plus the partial. Remember, we have x, y, z, and t. So we've done for x plus, we've done for y plus. Then what should come here? Someone to tell me what should follow. It is the partial change in u with respect to the z times the small change in z plus the partial change with respect to time times the small change in time. Okay, and then from here, this is known as the total differential equation. So let us divide throughout by dt, okay? So divide each component by dt, divide by dt, divide by dt, dividing by dt, we divide this one by dt. Remember, this dt into dt to give us a 1. So look at the first part here. We have the change in velocity with respect to time. This is called acceleration by definition, the change in velocity with respect to time. So this is going to be acceleration, but remember, this is the velocity component along the x-axis. So this, let's call it acceleration along the x-axis. So this becomes the acceleration component for the x-axis, and then we write the partial u x times, look at this, dx dt, change in distance over change in time. This is the velocity. Okay, now which velocity is it? Along the x-axis, the y-axis, the z-axis? Let's look at the distance. This is the change along the x-axis with time. So this is the velocity component along the x-axis, and this is u plus the partial of u divided by y times, what about this one here? Change in distance along the y-axis over time. This is the velocity component of the y-axis plus partial derivative z times, we have plus partial u over t, but this is going to be a 1, so times 1, okay, times 1. So let's write this differently. Let's write this as ax will be equal to, instead of writing this first, let's write our u first, u partial u over x plus u, okay, I wanted to write my v first, we should write our v first, v u over y plus, we are writing the w second, I mean first, and then u z plus u t. So this is the acceleration component, okay, this one here, this is the acceleration component for the x-axis. Yeah, so if I ask you to find the acceleration component for the y-axis, you have to do the same. Get now, because remember we just got the velocity component along the x-axis. So for these velocity components here, for the y-axis, you can find the acceleration component. For the z-axis, find the acceleration component. So this is your homework now. Go and find the components for the velocity, solve it the way I'm solving it here. So similarly, we can find the acceleration component along the y-axis. Remember, even from this pattern, we can tell that for the velocity component, we are finding changes along the velocity, okay, along the x-axis. The velocity for the x-axis, we have u, and u there, and then we are just changing. We have v u w. So we have u v w. So we have u. The change will be for the velocity component along the x-axis. So x here plus v, velocity component along the x-axis, y plus w, velocity component along the x-axis is v, z plus velocity component along. So in a similar way, you can show that this is the case. You can also show that for the z-axis, what is the velocity for along the z-axis is w, x plus v w y plus w z plus the change w with respect to time. You can also show that in a similar style. Okay, so this is what we have here. We found the velocity components from this around, because I gave you these notes some time back. This is what is going on here. The acceleration components have been found like that. Okay, so we are done with the methods for describing the fluid motion, Lagrangian method and the Eulerian method. So now next, if is there any question, we go to the next thing, discussion. Any question? Okay, Esther, let me hear you, so that I can know that you are here. Not just you've just logged in without watching the lecture. Okay, I've seen this. Should I proceed to the next thing? Okay, I'll just.
Yes, sir, you can proceed.
Okay, thank you. All right. So let's look at types of flow. So the types of flow that we're going to discuss here, we have 6 of them. So 6 of them. We have number 1, the steady and unsteady flows, the uniform, non-uniform flows, the 1, 2, 3 dimensional flows, the rotational and irrotational flows, the laminar, turbulent flows, and the compressible and incompressible flows. Okay, if I may ask anyone who can say something about any one of these flows, what do you... Okay, let's go to the steady flow. So in a steady flow, the flow variables such as the velocity, acceleration, pressure, density at a point do not change with time. So let's go back to this page here where I was to this page here. Look at this. These components that we found here, the first 3 terms, let's concentrate on this one. This term here, this term here, okay, I should have used this one. This term here, this term here, and this term here, they are all talking about space. Okay, space plus, then the last term is talking about the change with respect to time. So acceleration actually has got 2 parts, too many parts, the spatial part and the time part. So the time part, let me write time plus space. Okay, so the time part, this time part is known as the time part, this is known as the local acceleration. Then this is known as the convective acceleration. Okay, so for steady flows, okay, the flow variables like velocity do not depend on time, on time. So where we are, so the change, have you seen here what is going on here? The acceleration with respect to the change, okay, in time is equal to 0. So the flow variables do not depend on time. All the changes will be equal to, with respect to time, will be equal to 0, because the flow does not depend on time, even this one, for a steady flow. Okay, but for unsteady, the velocity components like acceleration, they depend on time, and their derivatives are not equal to 0. Okay, change in density with respect to time, change in velocity with respect to time is not equal to 0. Unsteady flows, the flow variables depend on time. Let's go to the uniform and non-uniform fluid flow. So for the uniform one, okay, the velocity, the flow variables do not depend on space. Okay, they don't depend on space. So the change with respect to space for the flow variables is equal to 0. That's what we have. That's why we have a 0 there. But for the non-uniform, they depend on space. So a flow can be steady and non-uniform, or it can be unsteady and uniform. So the common form of acceleration that we usually come across is the change in velocity with respect to time. So this is, if this is about a fluid, this will be known as unsteady, and it will be uniform, because there is no change in acceleration with respect to the space coordinates or space. Yeah, I hope that is clear to you. Next, let's look at the rotational and irrotational flow. So the fluid particles, while moving in the direction of the flow, rotates about their mass centers, and the opposite is known as irrotational flow. So I can ask you differentiate rotational flow from irrotational flow. I can ask you differentiate uniform and non-uniform kind of flow, steady and steady, laminar and turbulent flow. So in a laminar flow, let me just go straight to the diagram. This is laminar. The first one is a laminar flow. The second one is a turbulent flow. Okay, the particles, the way they are moving, they don't move in a straight line. They move in a zigzag way for a turbulent flow. But for a laminar flow, they move in a straight path, and they do not cross each other's paths. That is laminar flow. An example of a laminar flow is when you are, let's say, you use a straw to drink some juice. Okay, that kind of flow that occurs in straws is those flows are laminar flows. Then a turbulent flow, any kind of a flow in which the, for example, if you go to like oceans usually they can have turbulent flow, and even from the word turbulent, there are turbulence here. Even those, we know when you're flying to those in Qatar, or when you're flying there, maybe the pilot said something like, yeah, we are just passing through turbulence, just relax, everything is gonna be okay, and enjoy the flight. Yes, these are the turbulence. So there were turbulence there. Remember, even air itself is a fluid. Yes. So let's go to, done the turbulent and laminar flows. Then compressible and incompressible flows. So compressible flows, these are type of flows in which the density, okay, changes from one point of the fluid to another, and this can be caused by the pressure. Okay, the brake fluid that we use in vehicles, that fluid can be considered to be an incompressible fluid, because when you put the pressure from the pedal there, okay, it is almost instant. There's nowhere first where, so for example, if you have a fluid packed in this pipe, then this end is closed. If this is a fluid, okay, and then you press it with the, you put some pressure here. Suppose it's an hydraulic jack. Then you put some pressure here to try to compress this fluid. If at some point this moves from this point to that point, if it moves, okay, there has been a change in the density of this fluid. It has been compressed by this amount. So this kind of fluid which can move under pressure, which can be compressed like this, is called a compressible fluid, and those kind of flows are compressible flows. But mostly most fluids are considered to be incompressible. Okay, yes, let's do an example. All right, let's do an example. It is we're saying that in a fluid the velocity field is given by this. So we have a velocity vector here with I, J and K. So these are indicating that this is along the x-axis, the y-axis and z-axis. Remember, vectors, they look like this. Then our I there, our J there and our K there. Okay, these are vectors. This one goes there, I, J and K. So determine, the question is saying determine the velocity components U, V, W. So we said U will be indicating the velocity along the x-axis, V the velocity along the y-axis, and W the velocity along the z-axis at any point in the fluid field. And then also determine the speed at point 1. Then determine also the speed at time t is equal to 2 seconds at point 0, 0,2. Also classify the velocity field as steady or unsteady, uniform or non-uniform, and 1, 2 or 3 dimensional. Okay, so this is a fact question. So I know it is pre-solved in the slide, but let's do it from here. Let us do it from here. So let me copy that. So from here, remember I said this is x, this is x along the y and along the z. So the velocity components will be u will be given by 3x plus 2y, then v will be given by the one for the vector j, okay, 2z plus 3x, and w will be given by 2t minus 3z. We found the velocity components. Number 2 is saying that find the speed, determine the speed. Remember, speed is the resultant velocity, okay, which is the scalar part of the velocity. Velocity has got direction and the what is it called? It has got the quantity or the scalar and the direction, but speed is just the resultant, the scalar part. So speed is the resultant velocity, which we said should be given by the square root of the sum of the squares of these velocity components. That's what we said. And then this is the speed at 1, 1, 1. We don't know what the value of t is. We do not know. So let's find v, u at 1. We substitute where there is x. This is x, y and z. We don't have t. So where there is x, we are going to put 1 plus 2. Where there is y, we put 1. This is 5. Okay, Let's find now the velocity component along the y-axis. We have what is 1 there plus 3. We have a 1 there. This is also a 5. Then for w, we should have 2. We do not know t. Okay, we don't have t. So 2t we maintained, minus 3, 1 there. So this is just going to be 2t minus 3. Then we substitute each and every one of them here, there, and there. So let's do that. So the speed will be given by the square root of 5 squared plus 5 squared plus 2t minus 3 squared, everything under one root. Then let's simplify. We have, this is 25 plus 25 plus, if you expand this, let me expand it on the side here, 2t minus 3. This is square, so we should have another 2t minus 3. If you expand this, the first term times this, again this times that. Okay, again you start, so let's do that. 2t times 2t, you get 4t squared minus 2t times 3, 6t. The second part will be this term times this, and then this again times the last one. So 3 times this 2t minus is going to give us 6t plus 9. So this is 4t squared minus 12t plus 9. So this is 4t squared minus 12t plus 9. Everything under one root. Then we have a square root of, this is going to give us 50, these two, plus this 9 here is going to be 59 plus 4t squared minus 12t. Okay, so this is the resultant velocity. We don't know the value of t, so we just leave it there like that. This is the resultant velocity. So the second part is saying that determine the speed at t is equal to 2 seconds with these, at this different point. Here it was about at 1, 1, 1, 1. Now at here at 0, 0, 2. So we need to find the velocity components at this point. Okay, we know we have the velocities here. We have them here. Let me create some space here. Okay, so we remember we're looking for 0 and 2. So u will be given by 3x is 0 plus 2y is 0. So this is basically 0. So u is 0. What about v? Is 2. What is z? Is 2 plus 3, 0. So v is 4. Then what about w? 2. We've been given time to be 2 seconds, minus 3, 2 again there. So w will be given by 4 minus 6 minus 2. Okay, so the resultant, the speed, will be given by 0 squared plus 4 squared plus negative 2 squared. So this is going to give us, let me do this, this is going to give us 16 plus 4. So square root of 20, square root of 20 units, square root of 20 units, meters per second or meters per second. Okay, so we found the speed at this point, and then the question is also going further to say classify whether the velocity, classify the velocity field as steady and unsteady. So is it steady or unsteady? So how do we know? Is the flow variable dependent on time? If the answer is yes, then it is unsteady. If the answer is no, then it is not steady. But the fact that there is time involved in this equation, then the flow is steady. Okay? Sorry, is unsteady. Is unsteady because there's time involved. Now, next, is it uniform or non-uniform? The question to ask is, are the flow variables dependent on space? And of course, there are space coordinates here. There's x, there's y, there's z. So the flow is uniform. Okay, sorry, it's non-uniform. So be careful. Have you seen the way I'm also getting caught up with this? Okay, so it is non-uniform because it is dependent on the space coordinates. Next, is the flow 1, 2, 3 dimensional? The dimensions are x, y, z, and also time, because it's dependent on the x, y, z, and time. So the flow is a 4-dimensional flow. It's a 4-dimensional flow dependent on x, y, z, and time. All right. So let's go to, okay, these are the pre-solved, and then here the pre-solved questions in the same question. Then the part I wanted to do, the last part I wanted to do is the rate of flow or the discharge. This is the last part I wanted us to touch today. So let's just do this one and then we call it a day. Are we here? Okay, I see Esther has left the chat. Electro still here, Maurice still here, and Charles, they are still here. Okay, so discharge. What is discharge? Let me just before we even read anything here. Okay, if you have a pipe.
Yes, I'm just struggling with network. Can't see the screen.
Really? Yeah. I can. Even up to now, it's dark.
Can see now. Can see.
Okay. So now, about discharge, if you have, okay, let's say water flowing through this pipe, and then this is the nozzle, a very wide open nozzle here. So discharge is the amount denoted by Q. Okay, the amount of the water coming out of this pipe, the amount of the fluid coming out of this pipe. By the way, this amount which is coming out here is actually equal to the amount which is passing through this, let's say, area here, discharge, and it is given by the cross-section area of a pipe times the velocity of the particular fluid. If it is water, the velocity of the water. So this is known as discharge. And if you have got 2 points, 2 sections, okay, let's call this, let me cut here and call this section A, is section 1, and let's call this section 2, and let's call the discharge, the amount of water passing through here, as Q1, and the amount of water passing through here as Q2. Okay, suppose the area here and the area here are the same, so the amount of water passing through here at Q1 is equal to the amount of water passing through at Q2. Okay, this is the discharge, and this is known as the continuity equation. Also, it is also known as the continuity equation. Why it says it is dependent on the law of conservation of mass, and the law of conservation of mass says as the fluid, okay, parcel is moving from this point to the other point, the amount of mass it had at this point will be equal to the amount of mass it was going to have at the other point in a closed system. Suppose this is a closed system, the way I've written it. So the amount of fluid from that enters at this point will be the same amount of fluid that will exit at this point, provided there's no any other amount of fluid remaining within the system. Okay, so as the fluid moves from one point to another, the density, the mass does not change. The law of conservation of mass. Others like to say mass is neither created nor destroyed, something like that. But what I'm saying that as the fluid moves over time, the mass is conserved. So if you have a pipe which is like this, okay, so let's call is area 1, remember area 2, sorry, and then this is area 1, where it is entering from area 1, and it is flowing from here, going this way, exiting. The amount of fluid entering at A, passing through section A, and that of the amount of fluid passing through section A2, this is A1 and A2, these amounts, they are the same. So the discharge at 1 is equal to the discharge at 2. Okay, so remember, discharge at 1 is given by the cross section area at 1 times the velocity of the fluid at 1 will be equal to the cross section area at 2 times the velocity at 2. These are the same amount passing here and passing there. It's passing here and there. Okay, so this is the equation of continuity. Okay, so if you are given the cross section area at this one and the velocity, and you're given, say, the cross section area, this one, and then you're asked find this velocity, you can easily do that. Make velocity at section 2 the subject, which is going to give you this. Okay, so the same thing can happen if you're given any of the 3 things here. You can find the missing one. Okay, so let us go. Let's proceed. Okay, let's do an example on this. I think this diagram is showing at section 1, 2, the amount passing here is equal to the amount leaving from here. What is different is, one, the velocity here and the velocity there, and also the cross section areas. But when you calculate at this section and also at this section, you get the same value, the same quantity, the same amount of fluid flowing through those 2 sections. Let us do an example. So now in this example, the question is saying that the diameter of a pipe at section 1 and 2, the diameters are 200 millimeters and 300 millimeters respectively. If the velocity of the water flowing through the pipe at section 1 is 4 meters per second, remember the SI units are the meters per second for velocity, and then for distance it is meters, but we're given millimeters, and we know that 1 1 meter is equal to 1,000 millimeters. Okay, 1 meter is equal to 1,000 millimeters. Yeah. So the question is saying find the discharge through the pipe and the velocity of water at section 2. So the question which is posed is saying that we have, okay, a pipe. We don't know exactly what the first part is smaller than the last one, okay, because on the other side they're saying that at this section we have 300 millimeters, which is equivalent to, you divide by 1,000 to get in meters, you get 0.3 meters. This is a very big pipe, and then on the other side here at section 1 we have 200 millimeters, which is equivalent to 0.2 meters. Okay, and the water is flowing like this, and then they are saying that at section A the velocity v1 at section 1 is given by 4. Find the discharge. Discharge is given by the cross-section area times, okay, the velocity at the velocity. So we can find discharge using section 1 or using section 2. And at section 2 we don't know everything. We don't know the velocity at section 2, but we know the velocity and we can find the area at section 1. So how do we find the area? Formula for area is equal to pi diameter squared over 4. So in this case we're talking about the diameter section 1. Let's call it D1, and we're given the diameter, so the area will be given by pi times what is the diameter is 0.2 squared, 0.2 squared over 4. So the area will be given by, if you do that, I hope you are sitting somewhere with a calculator and taking the notes. Divide by 4. Okay, I'm not really a fan of decimals, but so this is pi over, so just evaluate, see this one and see what happens. Keep the pi over 100, or this is 0.031, and remember you don't round off these immediate number, you round off the answer, the final answer, not these ones. These are part of the computation. You don't round them off there and then. Okay, so write in full the way you see it on the calculator, or if you want you can just work out these ones and then get this 100 pi. So that is the area at A. So the discharge along this pipe will be pi over 100 times what is our velocity at A is 4. So the discharge will be given by, we know 4 there it is 1, then 4 there it is 25 times, so pi over 25. If you want you can write for area A this, the full figure here, the full figure. Don't round off to a decimal. Write, it is an intermediate figure, it's part of the computation, write it in full. Then what is pi over 25? This is 0.12566376061. So before you round off, we'll be rounding off to 3 decimal places. So before you round off, then you write first and 4, then you round off 0.2, 0.12, 3 decimal places, 1, 2, 3. but the number just after 5 is 6, so you get a 1 from here, put it on 5, you get 6. Okay, 6 cubic meters per second. These are the units: cubic meters, the volume, the amount of volume, or the volume of water which is passing through that section of the pipe per every second. That is discharge. So now the other part of the question is saying find the velocity at section 2. Remember, discharge at section 1 is equal to the discharge at section 2. Section 1 we have acceleration at 1 times velocity at 1. Section 2 we have area, not acceleration, at 2 times the velocity at 2. So they're asking for this one. We're being asked for V2. So V2 can be found by dividing this over this. Okay, but if you want, you know that this is just discharge at 1, so you can just 2 will be given by just discharge at 1 over the area at section 2. Let's find the area section 2. Remember, area is equal to, it is common written as pi r squared, but us will be writing pi d squared. So we're talking about the diameter at section 2 divided by 4. So let's substitute. We have pi times section 2 is 0.3 squared divided by 4. So let's evaluate that. So we have pi by 0.3 squared over 4. So this is equivalent to 9 over 400 pi, or in points the area at 2 will be given by, so you get the right everything 0, 7. I don't want to see people rounding off, especially those who are not attending the class. 3, 4, 7, 1. Me, I'm writing in full. Okay, so we're going to write the whole number, the entire number, V2. So I'm going to demonstrate here. Suppose you want to divide this, you write the entire number, the 0 point, that number here, this one, there, 0.1256637 061. This is 0. Okay, divide by 0.07068583347. Then what are we getting after this? What have we? So the velocity at section 2 will be given by 37061. Will be given by 0.1256637 divided by it's going to be 1.7777777 like that. Okay, so you can round off. We are saying that 3 decimal places, 778 meters per second. So this is the velocity at section number 2. Okay, let us go back to our slide. Okay. Okay, this was our problem and we just finished solving it, so we're supposed to, this is how it was solved, pre-solved. I'm sure you have gone through it, and we are now supposed to do the continuity equation as described by the use of partial differential equations. So in the next class we are going to start from here, so let's end here. Next class will begin from here, from this description. Okay, thank you for everyone who have managed to attend this class. Whenever you are free, so let's meet and let's finish off this. Yeah, is there any questions, any concerns?